me share the screen. All right. Is it visible to everybody?
Yes,
You
sir.
have to just remind me if it is visible. And you also have to tell me if, just a minute, I will use a pointer and hopefully that's also visible to everybody. Okay, I'll come back to that. I'll come back to that. Okay, so a quick recap of what CRM taught in the last class is that you can represent a, uh, a light switch control mechanism in the form of a Boolean algebra rule or Boolean algebra formula. So we have the following quantities which we call as Boolean variables taking values 0 or 1. So X represents if the light in a room is low or not. So if it is value is 1, it means that light in the room is low, and 0 otherwise. And U is a kind of switch which you can turn on or off. Similarly, if the value of U is 1, the light is turned off, and 0 the light is turned 1 the light is turned on, and 0 the light is turned off. So naturally you can see one simple rule can be if the room light is low, that is X is 1, it means that you turn on the light. But naturally you can see that this will lead to an oscillation because moment the light goes low, you turn on the light is high again, so X becomes 0, and then that leads to turning on U. So this will lead to oscillation. We don't want that. That's not a desirable situation. So what we do is that we can take care of that by introducing another Boolean variable L, which indicates whether light is on or off. 1 meaning on, 0 meaning off. So now the rule U, which you can think of as kind of an output, is X or L. So either the light is low or the light is on. In any of these two cases, it means the or the room light is on. Any of these two cases will lead to turning on U. So this way you see the light will never turn off because if there is enough light, still also it is turned on, so you no need to put it off. So this will indicate this will ensure that the light is always turned on. Now we also took another variable which is Y, which denotes the light outside, the environmental or ambient light. So this is again 1 if there is enough light outside, and 0 otherwise. So now you can if we consider also the light outside, and if the requirement is such that either the light should be turned on, the bulb should be turned on, if there is a low light in the room, and or there is not enough light outside, and there is not enough light outside. So naturally, not enough light outside means the complement of Y bar, and the second condition. So if we read the line that if we read the line, if the room light is low or the light is already on but not enough light outside. So the fact that this part, that light is already on but not enough light outside, can be represented by L and complement of Y, L and Y bar. So now, so if any of these two cases happen, that is either room light is not enough or the light outside is not enough and the light is already on, any of these two cases, so U is turned on. So naturally, you can express this as X plus L in L and So by the way, OR we write as plus and AND we write as product, multiplication, dot. So x plus L dot y bar, that would give the output U. Okay, so this is fine. And we already discussed in the last class that this is not the only way to represent the variable, the outcome of the variable U. There are many other ways. For example, if you write X or L, so either the light is low or the light is already on. This, or the light is low, and the light is low or the outside light is not enough. In any of these two cases, that is the second line of this, that is also another way of writing this. So there are two, we can already see two different ways of writing this. And how do I know these two are equivalent? You take help of something called a truth table, where the truth table typically is like this. You have first the columns corresponding to the input variables, in this case X, L, and Y, and the last column, we have two last columns here, is the output, which is typically an expression involving the input variables, Boolean expression involving the input variables, the truth value of those. And it lists all possible combination of the truth values of the input variables and the corresponding these values of the output variable. So if you write down the truth table for the first expression, you get this row or this column, and the second expression you get this column. And naturally, if these two exactly match, that is for the same input, both of these expressions give the same output values, then we say that these are equivalent, which is what is happening here. In fact, not only this, you have several other expressions. For example, x dot x plus L dot x plus x dot y bar plus L dot y bar. All of these are equivalent. All of these would lead to the same truth table. So naturally, one question that will form significant part of the study in this course is which one among these to be used. And our considerations are, you should do this using as small a circuit as possible. You save on not only on money, but also on the size of the circuit, the size of the chip or its the miniaturization that is possible. There are more advanced considerations that people use. For example, which of course we will not discuss in this course, which consumes the least amount of power, or maybe even more other considerations like which has the most fail-safe representation and such kind of things. So there are many considerations. Which the simplest one we'll see is which requires the least amount of circuit to compute. And because our goal primarily in this course, the objective of this course is to in such a situation where you have to control a light bulb and this kind of thing, you have to finally make a digital circuit which will implement this. Okay, so this is nevertheless a very simple case, but you can have more complex case. For example, you want to control the, let's say, a lift operating, an elevator operating with different floors where it may have to stop and start. So there may be more. You have to implement such situations in a circuit. That's the ultimate goal. Okay, so let's take a slightly more complicated case where it's more in the sense that you go more towards an automated implementation where you directly don't know whether you have light outside, enough light outside or not. Instead, you have three sensors, y1, y2, y3. So you directly cannot measure y, which is enough light outside, but instead you have three sensors, y1, y2, y3, which are kind of photosensors, which will just give an output 1 if there is not enough light and 0 otherwise. And depending on maybe the placement of these sensors or their functioning capabilities, all of them might not give the same answer. All of them may not give the same value 1 or 0. And we don't rely on any of them individually. What we do is that we rely on the majority. So if the majority says 1, 2 out of 3 says 1, it's 1. If 2 out of 3 says 0, it's 0. So this also you can see, this rule that if we denote the majority by y, so y is the value that the majority of y1, y2, y3 produces, you can represent that also by a Boolean expression. So you look at this formula. So y is y1 times y2, y1 dot y2, y2 dot y3, y3 dot y1. Okay. So what does this mean? If the so this is an OR of 3 terms: y1, y2, y2, y3, y3, y1. So when will this expression be 1? If any of these odd terms, y1, y2, or y2, y3, or y3, y1, any of these terms is 1. You know, the OR means if any one of the term is 1, it is 1. And when is any one of these 1? Any of the one of this 1 is any of these products are 1 if both the terms in the product are 1. And in both the terms, so either y1 is 1, y2 is 1, both are 1, or both y2, y3 are 1, or both y3, y1 are 1. Or it need not be any one, it might be more than 1 also. For example, all 3 y1, y2, y3 may be 1. So then each of these terms in the OR expression will be 1. But you can see that the minimum that you need is that any pair, which is a majority, 2 out of 3, is 1, then this expression becomes 1. So this is a nice way where you can represent the majority function. So now if we want to go back to our original U, which was earlier, let's go by this expression x plus L times y bar, which is when the light should turn on, bulb should turn on. You replace y bar, because now y is not so easy to get. You have to get it by the majority of 3 values, y1, y2, y3. Y bar is the complement of this entire thing, y1, y2 plus y2, y3 plus y3, y1. And we'll see that that this is equivalent, the bar on the entire or expression is equivalent to bar on the individual terms in the OR expression with a plus in between. Okay, with a plus in between. Okay. Okay, with a plus in between. So this, you know, is this can be easily proved again if you write down the truth table of the entire bar over the entire OR and this thing. This I think you have to check a little bit. Okay, so you will see again the truth table are same; they are equivalent. So this equivalence, what we have used is kind of a theorem or some equivalence which always holds, is called a De Morgan's theorem. So there will be a number of such theorems establishing equivalence between 2 expressions that you can easily prove by applying your by computing your truth table. But nevertheless, they are very useful from converting one expression to another expression. We will study them soon. We will study them. And why we are considering such conversions of one expression to other expression, with the hope that by a series of such conversions, some number of such conversions, because as we have discussed in the last class, the expression that we come up with often depends on our thought process. How you visualize, how a design comes up with a Boolean expression expressing a situation. But whatever be your thought process, what we will try to do is that whatever expression you have come up with, we will apply a set of such conversions to equivalent expressions, and finally get an expression which can be realized is in some desirable way, maybe minimum amount of circuit and other things. Okay, so that's the so this process is known as the minimization process, expression minimization process. Okay, so this is the first part of the course that we'll study. Next, we'll move. So what we are doing by virtue of this example is that this is apparently a simple problem. You have to just control the bulb in a room depending on the lighting condition. And we'll see that if you try to do a design of the corresponding digital system, digital logic, you will see that these are the steps you need to go through. These are the steps you need to go through. And this will be exactly reflected in our course coverage. We'll go through exactly the same set of processes, but indefinitely much more. We'll go through minimization, we'll go through realization and all these things, but with much more detail. And in the end, we'll do something which we have not explained here, because if we work on really large problems, which are not as simple as this light bulb, which cannot be manually computed and such way, you need computer-aided system, you need computer-aided software which will do this whole job of designing logic. It's no longer a single human being sits down and does this. It's a software which does this, and then there how to build the softwares, what are the good representations for such softwares, and so on. Okay, so now let us come to a slightly more complex case, where we will see that such simple logic might not work. We need something more. Consider the situation that maybe there's a lightning outside. Maybe there is a thunderstorm and there's lightning outside, and the external light, maybe for a second or two, is high. There is a flash of light and it is high. Since the previous expression that we have seen, if the outside light is high, maybe the bulb should actually turn on, because by the expression we have, by the logic we have, the outside light should turn off. Okay. Any question you have? No. The outside light should turn off. But we don't want that, because this is really a momentary thing, and maybe after 1 or 2 seconds pass, it will again be a cloudy situation with not enough light outside. So how do you do? Don't take immediate action. You wait for some time, see if the external light stays on, and if it does stays on, maybe you can turn off the light. But if it doesn't stay on, the sun has not yet come out, it was a lightning, if it does not stay on, you should not turn off the light. And the moment you do this, you have to have some kind of memory over time, because we are saying that it's momentarily high. Okay, it's not there for a long time. This means the moment you say that it is not there for a long time, you need to have a memory of what happened in the past. Was it on? How long was it on? You need to have memory. Okay, so we need to have a circuitry or mechanism or some way to have memory. In other words, we need to take care of the time. In this case, time. In other case, it might be something else. We need to have memory. Okay. Okay. So what is the solution for this? Whether that light goes up momentarily, then you need not turn off. What is the solution for it? One maybe human-like solution is like that. You sit with a stopwatch. Moment there is a lightning, so the light outside is high. You start counting the stopwatch. You put the stopwatch on, and you go on till the lightning is over. That means there is no bright light outside. You turn the stopwatch, and you see how long this went on. Maybe it went on for 1 second or 2 seconds or 1000 millisecond or 1200 millisecond. Your stopwatch counts that, and then you decide that, okay, if it was on for maybe 1000 millisecond, then I should not turn off. It is on for more than 1000 millisecond, then maybe I should turn it off. Turn the light off. No need. It's sunlight. It's not lightning, because lightnings are on for at most say 1000 milliseconds. So this kind of decision you need to take. How do you take this decision? You initiate another variable C, which kind of remembers what has happened in the past. So we call, let's represent that variable by C. This C is 0 when we are not counting the time. As you have said, maybe, just for visualization, let's say you have a stopwatch which is counting. When the stopwatch is not counting, we say C is 0, and when it is counting, we say C is 1. And how this count, or how much time has elapsed so that the light is still high? How do you do this? You do this by a finite number of states in a machine. That means you can imagine it like that. If you look at the output of the say the stopwatch can count only say 60 seconds, or let's say it can count only say up to 5000 milliseconds. So it goes 1, 2, 3, 4, 5 up to 5000. So you can imagine these values 1, then 2, then 3, then 4, then 5. Well, we usually look at it as time, the time elapsed in say milliseconds or something. But you can also think of these as the states that the watch is going, or the counter is going through. It's going through states 1, 2, 3, 4 up to 5000. So you have 5000 different states, and the clock or the watch, what it is basically going through is that it's moving from one state to another, and it can only go till 5000 states, then it will come back again to the one state. Okay, and now if I look at the state of the system, if the state of the system is something less than 1000, we'll put up the light. If the state of the system is in a state which is more than 1000, maybe we'll put on the light. So just by looking at the state of the system, you can, so it is a very nice way we have taken care of time. We say that, well, something has a state, some circuitry has a state which transits, which changes at some time interval. So it changes, let's say every millisecond it changes. So millisecond is kind of what we call a clock. Every millisecond it changes, and up to some max. And then depending on the state of this circuit, or whatever you call, depending on the state, we can take that, we can use that state. We can use that state, and that state will give us a memory about the system. Will act as a memory about the system. For example, if the state is greater than 1000, it carries a memory for the past 1000 milliseconds the light was on. Or if the state is let's say 2000, it will say that for the past 2000 seconds it is on. Okay, so it's in a very simple form captures the memory. It just captures how long the light was on. That itself, only that memory it captures. But that is enough for us, for our purpose, because we are just interested about how long we have enough light outside. Okay, So this you can design such. We said that these states change at some time interval. This can be represented using what is counter, a digital circuit. A digital circuit, which you'll see how to do that. So that's the next part of that we will study. This can also be something like a monoshot multivibrator, which are built using op-amps. So these are some circuit which changes between two states. It changes between two states. Okay, so this is fine. We'll come back to our implementation of these systems. How do we build a digital counter? What is a monoshot multivibrator? We'll come to this. In fact, monoshot multivibrator will not much use. We'll mainly be concerned with the digital counter. But what we'll see is that this counter or this memory or these states, they have a nice formalism. They can be represented very nicely as a digital circuit, as a kind of a block. So let's consider a simple case of a counter, which is just yeah. Please tell.
Sir, how will the system know that there is lightning and it has to start the clock? Like if it always keeps
so that
the clock,
we are assuming there is some sensor for that. Okay, we are assuming some sensor which kind of moment you have a so the sensor doesn't know it's lightning or something. Moment there is a bright light or there is light which is not which is enough. Let's say bright light. It starts counting.
It is just the external light sensor, nothing different.
Okay.
And distinguish between outside light and lightning. If the counter is
outside. Yeah, it's see, our definition of lightning, we are not really bothered whether it's lightning or not. We place a sensor outside. Moment a bright light comes on, will start counting. Moment bright light goes away, it starts counting.
okay.
Okay.
So don't we count latency in system?
Repeat. Hello.
So don't we count latency in system?
Yes. So exactly, that's an important point. So that's the answer is like this. So that we don't really differentiate between time less than 1 millisecond. Don't bother about time less than 1 millisecond. Okay. So we have a clock. We have a clock which ticks every millisecond. So we want to, as if we want to count our time is a integral number in terms of milliseconds. It's say 1000 millisecond or 1200 millisecond. It's not 1000.12 millisecond. We are not bothered about time quanta less than a millisecond. It doesn't matter if the light is on for another 0.12 millisecond. We don't bother. Okay, so that's the important point. So this counter changes state only every millisecond. The state change it cannot happen in between. It cannot happen at 1000.12 millisecond. It happens at 1000 millisecond, and the next time the counter changes state is 1001 millisecond. Nothing happens in between. Nothing happens in between. Okay. So if this is the situation, if the state change happen only in 1000 and then 1001, then 1002, then 1003, we say that this system, this counter is synchronized with a 1 millisecond clock, a clock which changes state 1 millisecond. Okay, so now this 1 millisecond may be too high. For example, in your laptop or computer, the clock that you have has a frequency of say 2 gigahertz, which means the clock there counts only in quanta of 1 by 2 gigahertz, whatever that number is, much less than a millisecond, much less, maybe nanosecond or something, I don't know. 1 by 2 gigahertz, that means 2 giga counts per second. 2 giga counts per second. Okay, so that's the resolution of the clock. So it deals with time quanta that small. So in your computer, whatever counter you have, that will change state only in those time instances. But the thing is that so your clock speed, so to say, your clock speed with which your counter is synchronized, will determine how fast an event you can handle. So in this case, maybe a 1 millisecond clock is enough for the lightning. We don't need more time. But maybe if you are counting, say atoms in a cyclotron or something, then your digital counter should be, say, femtosecond, even less than what your computer has. Your clock might be even less, even faster. Okay, but the whole idea is we don't really bother about it's 1 femtosecond or 1 millisecond. What we bothered is that, so we can decouple this. So your counter will state change only at this time instances. It's synchronous with this clock. Whenever the clock changes, only then you can do something. You cannot do some. So this has its advantages. You can naturally see that all these things, that what will happen in between, these problems are no longer there. Everything happens at the clock. Any change happens only when the clock ticks. Okay, and is this clear? So it's basically you have a clock which measures time at some interval, and that clock controls or decides when this change in state can happen. This is a nice situation then, because you can sort of, you need not bother about what happens in between. You only look at the system on only these points. Okay, this makes the circuit simple. The other case where it can happen anytime in between the clock, there is no clock as such. There is nothing to maintain time. It's called an asynchronous system. It's kind of event driven. It's not clock driven. It's like the situation, your class starts at 8 or 9 or 10 or 11 or and so on. And only at 8 or 9, your one class will, at 8 o'clock, one class will start, at 9 o'clock it will end. At 9 o'clock, another class will start, at 10 o'clock it will end. So this is a good situation for you, because you have to get out of your room or hostel and come to the class only at 10 or 11 or 12 and things like that. And this is a synchronous system. There is a clock, the IIT maintains a clock that 10 o'clock it will happen or 11. But suppose we don't know when the class, maybe some class starts at 8:15, it ends at, say, 8:51. And then the next class starts at 8:52 and ends at, say, 9:12. So you really don't know when classes are ending and another class is starting. It will be very difficult for you to manage. You really don't know when to go to class, when to move to another class. You don't know when things happen. It will be a complete chaos. Well, it may be event driven. For example, it may be the case that whenever a topic ends, the class ends, and then another class starts. This is kind of event driven, not synchronous, asynchronous. The event is that a topic has ended. You need more circuit to handle such situation. The circuits become more complex, but they are used. They are definitely used in some places. Okay, so let us come back to the synchronous counter. Let's say we represent a counter by the following thing. Let's say we represent the counter as follows. For example, in the stopwatch case, you are saying that it counts to 1 to 5,000. So I can represent 1 to 5,000 in the decimal way like this. Say 1 I represent by how many? 4 digits. 0001, 0002, 0003, and then after 9 it will become 0010, then 0011, and so on. So you see the digits are increasing by 1. First the least significant, then the second least significant. These digits are increasing by 1 as the counter changes the state. So instead of decimal, naturally in a computer we will not have decimal, but we will have binary states, bits. It will be a number of bits, and these bits will change from 0 to 1 and so on. Let's say we have a Boolean variable z, which is 1 when all the bits are 0. That means the counter is in its initial state. All the bits are 0, and 0 if it is not in the initial state. At least one of the bit is different. And what we'll have is that we'll have a countdown. That means we'll start from high value and count down. So C is a variable. We call it a line, which if set to 1, it's counting down. It's counting down. So maybe it's countdown. Then all 0 is not the initial state; it's the final state. If it is countdown, all 0 is the final state. So C means it has begin countdown from the maximum state, and R means a reset. That means it was counting down. It is in some intermediate state. For example, it's counting the bright light due to lightning. So it has started from say 5,000, this counting down 4,999, 4,998, and if it comes to 0, that means all 5,000 is over. Or okay, you can actually make it even simpler. You know that lightnings are there only for 1,000 seconds, so you can have a 1,000 millisecond countdown. So you start with 1,000, then you bet 999, and when you reach 0. If you reach 0, you know, and still the light is on, you know it's not a lightning, it's a sunlight or something. But if it becomes all 0, and before it becomes all 0, maybe the light has come down, it means your count is, you need not count anymore. It means that it was a lightning. It did not stay for 1,000 milliseconds. Okay, and then you have to restart. You have to restart again for the next lightning. So you have a line R which reset it to all 1. Okay, so these are kind of the external signals which will either decide whether your light bulb inside the room should be turned on, which Z will decide, or which is triggered, which changes value, C and R, they changes value depending on the light sensor, let's say. Okay, for example, if there's a bright light sensor, C will be turned into 1, it will start the countdown. When there is a no longer bright light sensor, then R will be set to 1, it will reset again back to the all 1 count, all 1 state. So these are kind of external signals. This comes from the sensor. Either they come as input from the sensor, or they go as output to the light bulb controller set. Okay, so these are external. These are signals. This external, which the variables which come from outside, we call them as signals, as if they are coming from somewhere else. They are signals, and then there are states of the counter, which is internal to the counter. It's a property of the counter. It's called a state of the counter. Okay. So let's say what are the states that a counter can be in. You have a normal state, which is a kind of, it's not counting. It's a sitting idle. It's not counting. You have a state or a start state or a get ready to count set where the counter is set to maximum. Okay, it's all 1, all bits 1. It is a D state. See, you see these states are kind of, they are the ones which hold a memory. They are the ones which has a memory of the past. Okay, And you have a D state, which is that means the counter is counting down, and you have a C state, which denotes that the counting is over. It has come to 0. All bits have come to 0. Count down to they have count down to 0. Okay, so these are the 4 states that the counter can be in. Can either be in a normal state, not count. It can be in an initial state, that is ready to count S. It can start the countdown D, and you can go. So naturally, you see, if you see the sequence of states that will happen normally, it may be other sequences also. It is usually like this. It will start from S, then go to D, then go to C, and then maybe go back to N. Or you can also think of this like this. You start from N, then once it is reset, it will go to S, and then countdown will start. It will go to D, and from there it will go to C when the counting is over. So all this will happen at different point of time, synchronized with the clock. Maybe N happens at say if you count from the start of the day, it happens say 1 lakh 1 millisecond time N happens, then 1,01,02 S happens, then 1,01,002 D happens, then 1,01,003 C happens. But everything is at the tick of the clock. Okay, so so this is point, and the second is there is a sequence in which the counter moves from one state to another state. Maybe the state changes. This will depend on 2 things. First thing, it can only happen at the tick of the clock. Second thing, this will be triggered, or this will happen. That means N will go to S. When will N go to S? When there is lightning or bright light, whatever. Okay, so that means when C is turned on. So these state changes, not only they happen at the tick of the clock, they are also triggered by the signals. They are triggered by the signals, right? Okay, so we can kind of represent it like this. So the first column, this is not exactly a truth table. I should say this is a state table, we can say. So it's like this. If the previous, now we are looking at the state of the counter. If the previous state, which is this PS column, is N, the new state will be S only when the input signals, only when the input conditions are light is 1 and the output light is 1. Only under this input signal will a normal state go to the startup count state. Okay, and if the input signal is 0 or L equal to 0 or Y equal to 0, then it will continue to stay in the normal state. No change will happen. So if the previous state is N, new state will also be N.
Yeah,
similar. Yeah.
You can say that PS is the present state, NS is the next state. Yeah.
Okay. Yes. NS is the next state. And these state changes happen at the clock, and which state it will in the next state will be from the current state will depend on this input conditions. Will depend on this input conditions. All right. So there can we complete this table for the other previous state and the next state pairs. If the previous state was start and the next state is D, it's always you don't need any input condition, it will naturally start. If the previous state is D and the input is Z, what is Z? Z is the Boolean variable to indicate all bits are 0. That means counting is over. You have count down to 0. Say 1000 milliseconds, you have finished counting. If the next state you have finished counting, your next state is C. What is C? C is counting over. Your next state is C. If it is not yet over, that means Z bar, that means you have not yet come to 0, you have not yet count down to 0, it will continue to stay in this state. Similarly, if the count is over in the next clock, whatever is your input in the next clock, it will go to a normal state N. Okay, and also this is the previous state and the next state depending on the input conditions. Now you can see what is the purpose of all these state changes. You see that depending on the state of the counter and the value of the signal variables, you can decide what your output will be. Output in this case is U, that means whether to turn on the light or not, our original problem, to turn on the light or not. So you see, you can decide on the output, you can decide the output will be 1 or whatever expression will be. It can be determined using the input signals, that we have mentioned, that is this C and R, and the state. Okay. Say for example, in this case, when the next state is S, and if this is your input signal, that is C is 0 and R is 1, you can turn on the light. Okay. And if the next state is normal, then you can turn off the light depending on your input, indoor lighting condition, which is X and L and Y. Y is different, X and L and Y, X and L and Y, your input and Y is the output condition depending on these signal variables. Okay, so this way you can decide on the output by. So one thing you see that the expression for the output is different for different states. And of course it is different for different signal conditions. Okay, so you can decide your output based on this and the input condition. So there are two situations. If your output U depends only on the inputs, only on these inputs and the signal, only on the input and the presented, then we call it a milli-machine. If it depends on the state and the input, we call it a milli-machine. And if it depends on both, we call it a milli-machine. And if it depends only on the present state, not on the inputs, just the present state, we call it as Moore machine. Let me see if I can draw a simple diagram to sort of represent this.
In the meantime, I just want to draw your attention to that you're not only controlling the light bulb. Okay, so U is the line to control the light bulb. So in addition to controlling the light bulb, we are controlling something more also. So looking at this table, can anyone say what more you're controlling? Yeah?
The counter clock.
Yeah, you're actually controlling the counter also. So as you can see, sometimes you're turning the counter, you're resetting the counter. So sometimes before you start counting down, you want to first reset the counter, and then at some point you want to start counting down. So as you can see, you're also controlling the counter. So these are all So all the lines which are set by your machine, those are called output. So these are all output lines. So here you have got 3 output lines, and you have got certain inputs. So inputs, you can see this L is an input, Y is an input, and so on. So these are inputs, and then you have got outputs. So for a sequential machine, you have some primary inputs, you have got some primary outputs, you have got secondary inputs and secondary outputs. So secondary inputs and outputs are basically the state variables, and primary inputs are the inputs that you are getting to the system, and primary outputs are you can say the variables that you are controlling apart from the state of the system. So those are the primary outputs. Okay, yeah, please. So I think
yes, exactly. So that is I actually mean. So these are also what are the primary outputs. They should be, because they control the state of the system also, besides the state of the system.
Excuse me, sir, I have a doubt.
Yeah, please tell.
Could you go back to the previous slide? Like what was there
This
earlier?
slide?
Yes, sir.
This one?
This one only, sir.
Okay.
Oh, I meant the one with the table. It was lagging, so.
Yes.
Like there's when there is no input to change from a state from S to D, there's no input condition that will change it, and from C to N there's no input condition. So we're wasting a tick by staying in the state S and state C, right? You said the state changes only happens at each tick of the clock.
Yes, we are wasting a tick. So that's a disadvantage of the synchronous system.
Okay.
But we are definitely wasting a tick, but it helps you because it helps you in many other ways. You allow this wastage.
Okay. What is the necessity for two states here? Two different states, S and D. They both have to be the same thing, right?
Yeah, I'll just tell you over here. I'll just tell you. So that's an interesting question that you have raised, because when you see, let me just draw an analogy to the way you program. When you write a program, you write the program so that you understand what is happening. Okay. You don't try to write a program so that it will have the least number of instructions and all that. You think of how the program is. Your main focus is on getting your program correct. Of course, there are other efficiency conditions. For example, you might have a better algorithm. For example, instead of say bubble sort, you might prefer to use a better algorithm. That's a different thing. But when you write a program, you don't try to reduce the write it so that it will take the least number of instructions or something. You leave that to the optimizing compiler. So here also, when you design your system, for you what is more important is that you design it so that you understand how it's working, and you have some confidence that it is working the way you want it to work. Now it is possible, in fact what you pointed out, that is possible. It is possible that you have some redundant states, but we'll in fact look at state ways to optimize your state machine so that redundant states can be identified and they can be merged.
So that is kind of again equivalent to a compiler optimization.
Yeah. So the point that you raised is relevant, but again, what we'll say is that when you design the system, you focus on the elegance, the simplicity of your design, the correctness of your design. We are also going to study state optimization technique, but that is a mechanical process. So we'll leave the optimization to the algorithm that optimizes the number of states. Okay, yeah.
Okay, sir. Thank you.
So that's an interesting question, because we'll do study. In fact, we can see that there are nice algorithms which will, this you have observed, there are nice algorithms which will automatically identify such redundancy.
Okay, sir. Thank you.
Okay, so so there is another way you can do the same thing, the states, but this time it's asynchronous. You use something called a monoshot multivibrator. You don't need a clock. It's something an event trigger. I mean, it's a multivibrator. Multivibrator means it vibrates between states. It can vibrate between states. And you don't need a clock. It can happen anytime.
Yeah, just let me just tell you, Monoshot. It's a very simple device. So let us say that its normal output is 0. Okay, the output of your monoshot is 0 normally, and then it has a trigger input. Okay, it has a trigger input. So once you trigger it, I mean, it's just a Boolean variable. Think of the trigger input as a Boolean variable. Say it is 0 if you are not triggering and 1 if you trigger. So the trigger is an edge sensitive, means if you leave it at 1, it is only the 0 to 1 transition which is the trigger. Okay, so it has a trigger input. So when you trigger it, the output goes high and remains high for a certain number of time. For a certain period of time, which is determined by the design parameters of the monoshot. So you just say that it remains high for some period delta. So that is how the monoshot works. And again it goes down. So its normal output is low. When you trigger it, it goes high. It remains high for a period delta. Again it goes low. That is the working of a monoshot. Okay.
Yes. So we can represent the signals related to the monoshot are, as Professor CRM has discussed. You either trigger it when it goes to 1, it goes to high, and then you have another line which turns this trigger on or off. So moment you trigger, it will stay high for a delta time and then come back to 0. Okay, but then there is another line to decide whether to trigger this monoshot or not. It's kind of a external line. So we have the following. We can use the following states. Again, see, what we are doing is kind of a design based on our understanding of this lightning problem. Based on our understanding, we are kind of doing a design. This is typically what we will have when this is called a domain knowledge. You look at the system, what the system requirements are, and all this. You analyze as a human being, and you come up with the following states. Then you come up with the following variables. You come up with the following input and output, and use that all this thing. You decide on this state transition table or the Boolean logic table. You form those. You have the desired state transitions, and then when we say it's a monoshot, these are realizations of this design. So this is what you have. Using this, you can realize. Then you come up with your design. You think of a nice way of doing all these things, and these would be the states. These are the states. This is how the monoshot behaves. So this will be your states. And using this and the input variables, you design your Moore machine. You design your Mealy machine, and that gives you the correct input output. That gives you the correct input output. Okay. So this is a process of designing. It does two things. First thing, what device you have. You have a counter or you have a monoshot. It will be determined by that, and it will be determined by the requirement of your system. That light should go on when lighting, all this requirement. So this it's based on these two. It's like you make the design. Again, referring to the programming. So you use a monoshot or you use a counter. It depends on like what are the operations you can do. Say you are programming in C, you have a certain set of operations. If you are programming in machine language, you have certain other set of operations. So this will decide what are the operations that you can use, and your program will be a solution to the problem. Maybe you are asked to find the GCD of two numbers. That's your problem. You write a program using these basic operations to solve that problem. And this entire, so this program is your design. In this case, it is design. Okay. So you as a digital designer, as a designer, you will form this state transition tables, these variables, what all variables you have to introduce. In this case, a single counter does, do you need multiple counters, do you need multiple monoshots? You do this design. And as you have rightly raised the question, then this design is not the final one which you box up and install in your for your lightning controller or something. You do a minimization, just like a compiler does an optimization. You do a minimization, and then come up with the final circuit, which we'll do in the lab, come up with a circuit. And that circuit, somebody fabricates it, somebody uses semiconductor to build that chip, and that chip is the final thing that goes inside your system. So the final output is that chip. This is what we are doing is the first step, the design step. After that, there is optimization, and then how to make the realization, and finally how to design the wafers, how to design the semiconductors, how there are a lot of optimizations there also, how to build the interconnects and all these things. And then after all this, even there are things like packaging of the chips and other thing. After that, your final product comes out. It's a long process, but this is definitely the first step. Okay, so if we the control states of the monoshot will be a normal state, which is z equal to 0, that is not triggered. The normal state of the monoshot, it's not triggered up to a higher state. S, it is triggered up, which is r equal to 1 line. That means it will trigger when the trigger line is 1. And this line will be 1, as you can imagine. It will be based on our problem. It will go to 1 only when either the lightning is low or the outside lightning is also low. Only then this will be triggered. So you see, this is not clock triggered. This is an event triggered. What is the event? Event is inside the light is low, outside light is also low. L is 1 and Y is also 1. Okay, so this event, this triggers the monoshot. This makes it 1. Okay, you don't wait for the clock. And then you have another state which is waiting for timeout. And this is when it's triggered. After that, z equal to 1, then it will go to this. It will wait for the timeout state. This is something inside the delta interval. This is some, so anything inside the delta interval will be in the D state. And then C state is this delta is over. You have come back to z equal to 0. Okay, now you can move on to the next state, normal state. So you see there is no clock here. The L and Y and then Z, these events determine when it should be triggered or not triggered. Okay, so what is the advantage of this? First advantage is you don't need this stopwatch kind of thing which counts down till 1000 to 1, 1000 to 0. It need not count down. You need not look at the watch clock. So many digits, 4-digit number, 4-digit decimal number, it's counting down. All those things you don't need. It's directly event triggered. L equal to 1, Y equal to 1, monoshot fires, triggers. It stays for some time, comes down. Okay, so that's the advantage. You can do that. Okay, but there are many other disadvantages also of this. I mean, of course, I mean, firstly, you need a monoshot which has many parameters to control. It's not as simple as the thing, but still you can do it. But the thing is, the point to be noted is that this is an asynchronous. There is no clocking here. It's just event triggered. In many situations, this is also desired, but see our considerations now. So we have so many options now to do this. Will also depend on what type of. Now it will come to the next stage, that what type of circuit you finally build out of it. Okay. So what we will do next is that we'll study some of the circuits involving semiconductor devices that will be used. Yeah, CRM, please.
So just okay. So Pabitra, I think you can. I will just.
I'll relinquish the control then. Maybe you can take over your control.
I will open that. Okay.
Wait, let me stop the sharing.
Yeah. Okay.
Yeah, I think I have stopped sharing.
Okay. So let me. I think I should share my desktop. Okay, I think you can see the desktop, right? So yeah, just I wanted to say one thing. So this monoshot is, you can say, a simple kind of counter. It's not very flexible, but it is just a, a circuit. I mean, it typically uses what you call an operational amplifier. You might have, if you are used to reading magazines like Electronics for You, so you might be knowing of a very well-known IC chip called IC555, which can be used to make a monoshot. So point is that sometimes a monoshot is a simpler option to a counter, but a counter is more flexible. So I mean, what I just wanted to tell you is that there are many design options which which if you are aware of, you can use to your advantage. That's all. All right. So let us just do a little bit of circuits. So as we said earlier, we will not be dwelling too much on circuits, but you should have some knowledge of circuits. So that is why we are just dealing with these at the beginning of the semester, so that you have some knowledge of how these things work. So first of all, present day semiconductors are all are usually made up of what you call Mosfets, or metal oxide semiconductor transistor, field effect transistors, metal oxide semiconductor field effect transistors, and especially CMOS or CMOSFET circuits. So CMOSFET circuits, so you have two kinds of transistors. You can see that you have one transistor here and another transistor here, and they are a bit different. As you can see, they're a bit different. So one of these is called Nmos circuit, okay, another is called a Pmos circuit. So in case of an Nmos circuit, the majority carriers, I'll just tell you, I'll recapitulate how it works. So majority carriers are electrons. So let us just look at your so this is your silicon matrix. This is a silicon matrix. So for such semiconductors, you normally use high purity crystalline silicon. So the atoms in this semiconductor, those are actually arranged as you can see in the diagram. They form a crystalline structure, and silicon is valency is tetravalent. So you can see that each silicon, it actually has 4 bonds. So in the middle we have put a phosphorus. So here in this matrix, you can have see, if you have pure silicon is not a good conductor, because as you can see, the electrons are all bound up in these bonds as shown over here. These are bonds, so electrons are bound up, so they can't really move. So pure silicon is not a good conductor. However, you can put some impurities. So the effect of this impurity is that, so you have usually two different substances. One can be phosphorus, the other can be boron. So the difference is that, so phosphorus is pentavalent, okay? Phosphorus is pentavalent, whereas boron is trivalent. So pentavalent means it has 5 electrons. So in this lattice, it can use up only 4 electrons. So this one electron here is free. Okay, it is free. It doesn't bind to anything, so it's free. It can move around. Okay, and because it can move around, it can also, you know, it can carry electricity basically. So it can move around. In the other case, when you have boron, boron is trivalent. Okay, so there is a deficit of one electron. All right, there is a deficit of one electron. So what can happen is, because you have a deficit, you know, so this is called a hole. This deficit is called a hole. Okay, so an electron from some other place can, you know, just you know, jump into this hole. So of course, if it jumps into this hole, then you have, you know, then what will happen is that you will have this place filled up after it jumps in, and you will have a hole over here. You'll have a hole over here. Okay, so basically you have you have a situation where your holes can move around. Okay, effectively a hole from here is moving to this place, and this can move somewhere else. So here your you know, here what you can have, your some electrons can move around, some electrons can move, and here you have some holes can move, right? This is the situation. So these are your, you know, majority carriers. Here your hole is the majority carriers. Okay, so this one is your majority carrier. And in this case, these are your majority carriers. So so this is your N plus. So N plus. So here, you know, where so this is a N type you know, material, and this is called a P type material. All right, this is a P type material. So N plus. So when you have N plus, or for that matter P plus, it simply means that you got more. This is heavily doped. N is lightly doped, N plus is heavily doped. P is lightly doped, and P means it is doped with something like boron, and N means it is doped with phosphorus. N plus means it's doped with more phosphorus, and P plus means it's doped with more boron. Now note that these doping levels are, you know, the levels are pretty low. These are you know, parts per million, or maybe even less. So that is the level of doping. That's why it's called doping. You have just parts per million, or maybe even less. So what is happening is, in this N plus, you have this sort of a situation, which is, you know, shown over here. So let us just draw it a little bigger over here. So what you have is this is, let us say, your substrate, your you know.
CRM, I think we have lost the presentation.
Oh,
lost
I have.
The
Oh, sorry. Yeah, thanks for the. Yeah, sometimes it goes off. Yeah, sometimes it goes off. Sorry. Yeah. Thanks for pointing out. Okay, so this is your substrate. So here you have what you call a p-type substrate. All right, and in that you have, you know, you can create wells. So here you have so inside this your so p-type means you got, you know, more of boron here, means it is doped with boron. It's doped with boron, and inside this you are basically, in this region you are doping with phosphorus. So you might have read of methods like ion implantation and all that. So you are just pushing in some phosphorus atoms here. So you are creating this, rather you are pushing in a good number of phosphorus atoms here. All right. So that's why it is you're indicating it as N plus. And over here, as you can see, over here you have a thick, you know, relatively thick layer of oxide. This is called SiO2. That's why it is called, you know. So this is SiO2. This is the oxide, you know. There's a Mosfet. So metal oxide. This is the oxide. And however, in a certain window, you don't have the oxide that thick. So this is, you know, you can say thick. And in some just over here you have what you call, this is also oxide, but this is, you know, this is thin oxide. This is thin oxide. All right, and this is, you know, this fabricated, so this is well aligned. Okay, this is well aligned, and over here you have a deposit. You have a deposit of what you call or maybe I can just use a different color. This is called polycrystalline silicon. So here means this is you can say a strong conductor. So here what happens is you basically have a strong conductor between these two N wells. Okay, and this N means, as you can see, these are electrons, right? So N means you can have what it means is that you have electron rich. Electron rich regions. All right, these are electron rich regions. So if you apply a high voltage, okay, so when you say, so normally, so this is a P-type, this is a P-type. So as you can see, under normal circumstances, no flow of electricity, okay, from this well to this well. No flow of electricity between this well and this well. So so this, let us call this as the gate, okay. We'll call it, let's call it the gate, okay. So one of this is called the source and the other is called the drain. Anyway, so these are two terminals of the transistor. So this is your gate. So G at low voltage means no current or no conducting path from source to drain. All right. Now, suppose you make G high. Suppose you bring it to a, so because now high voltage means this is electron rich, so you'll have some electrons coming here. You'll have some electrons coming here, and you have a channel. Basically, it forms a channel over here. So high voltage, leads to channel formation, because there is an electric field. When you put the gate at a high voltage, you have a strong electric field which attracts the electrons, so leads to formation of channel between source and drain. All right, so in other words, that's a conducting path. Okay, so you have a conducting path. You have a conducting path. All right, this is a conducting path. So current can flow between within the source and the drain. All right, so in other words, it's like a switch. If you turn the gate, if you set the gate to a high voltage, it's like a switch. It just connects the source and the drain through a channel. So you have a channel that is that's populated with electrons. So it just acts like a switch, and if it is low, this channel dissipates. You don't have this. These electrons are no more present. Okay, so that is how Nmos transistor behaves as a switch. Your PMOS transistor is so the PMOS transistor, it also behaves in a similar way, except that instead of electrons, you have holes over here, and and the behavior of the gate is that if this is at a high voltage, so your in your p-type, you know, in your p-type silicon, you have more holes which are positively charged. So if your gate is at a high voltage, it will repel those electrons, and on the other hand, if it is at a low voltage compared to this, then it will attract the holes. It will attract the holes. So just as a high voltage attracts electrons, so if you have a high voltage, if the gate is at a high voltage compared to the source and the drain, then the electrons are attracted to form a conducting channel. In case of a p-type transistor, if the gate is at a low voltage compared to the source and the drain, then the holes get attracted to form a conducting channel, and otherwise you don't have any conducting path. So it's kind of complementary. The operations are complementary. So once is this explanation okay? I mean, you must have studied this earlier. So any questions about the working of N and P-type transistors that was just given? Yeah. Any questions? No comments? Nothing? Have you followed it at least? Yeah. No reply. Aditya,
Yes, sir.
have you followed it? Okay, I hope I take it that you have followed it. So now that you know how these transistors work, so let us just see if we can explain the working of a very simple circuit, which is an inverter. So I'll just leave these annotations. I'll just open another instance of this.
I think escape will also maybe erase. Yeah. There is an button to erase everything. Okay, but this.
No, I don't want to erase actually. So I'll just leave it there now. Yeah. So let us come back to this diagram. So what you can see is that you have this is a p-type transistor. Okay, this is a p-type transistor. And this one is an N-type transistor. Okay, so let us just see what happens. So when A is high, okay, when A is at a high voltage, okay, then what happens? As you have seen, if you have a high voltage, then you're going to have a channel formed between the source and the drain, right? And this is ground. Ground is, you know, let us say that ground is at 0 volts, all right? So you have a channel to the ground. So in other words, this terminal, this output terminal, let us say, this output terminal. So when A is high, let us just call this the output. When A is high, if A is high, as you can see, let us see how it works. So it is going to form a channel, okay, and so that's a conducting channel. So this output, you have a conducting channel between the output and ground, so it's going to go low, okay. And what about this? A is high, so because it is high, as we said that when the gate is high, you don't have a channel over here, so this is open, okay. So we can say that let us just try to do it like this. Let us say A, P, this is N, and this is out. Alright, so this is high, P is open, N is closed, output is low. Alright, and if this is low, okay, if this is low, if A is at a low voltage, then you know that N is going to be open, okay, there won't be any channel here, so this will be open. This is low. If it is at a low voltage compared to the source and the drain, it is going to be closed, right? This P-type. And the output, so you have a path, you have a conducting path between the VDD and the output, so it is going to go high, okay. So that is basically how this inverter is working. So it's an inverter, okay, as you can see, if the input is high, the output is low, if the input is low, the output is high. So that is the basic working of an inverter. You can also think of this as a function. So you can think of this as a function. This is f of A equal to A, alright. You can think of this as a function f of A equal to A. So it is just a complement of that function, okay. So with this notion, let us see if we can let us look at some other transistor configurations. So let us see if you see what is happening over here. So you have two transistors in parallel, okay. These are of course you know, if you just notice carefully, what you'll see is that these are all N-type transistors here and all P-type transistors here, okay. So here what you have is you have got two transistors in parallel, all right. One is connected to A and the other is connected to B. And what you can see is that its working is a bit like the inverter. So if A is high, as you have seen, then you have a conducting path to the ground, so this will go low. And if B is high, then again you have a conducting path, so this goes low. So in other words, the output goes low when either A or B become high. So again, as I said, that if you think F A B, all right. So what is happening if either A or B become high, the output goes low. So this is really, you know, it is. And let us see, I mean, that is how, but we have to be careful about what's happening out here. So here again you see, if either of A or B goes high, then you have a disconnection, right? If either of A or B goes high, you have a disconnection. So that's all right. So that means it is actually, and if both A and B are low, then you find that you do not have any conducting path from this output to ground, but you do have a conducting path. If both A and B are low, you do have a conducting path from VDD to the output. So as you can see, it correctly realizes the NOR function, right? So if we just carry out the same exercise that we did last time, I would encourage you to do it in your own notebooks. So please do that. You can just, so you have got A, you have got B, you want to just know what is going on, P1, P2, you have got N1, N2, and you have got the output. So let us just see if let us say A is high, okay? So if A is high, what you see is that P1, if A is high, P1 is open, right? If A is high, P1 is open, right? And N1 is closed. Output is low. This is enough to make the output low, all right? And so it's enough to make the output low. So suppose B is high. So let us consider. So you have a similar situation. If B is high, then you have a similar situation. This is open, and this is closed, and the output is again low. And if both A and B are high, you find that the output it's a merger of these two lows. So output continues to be low. And if both are low, then what happens? Then both P1 and P2 are closed. Open. And the output is high. All right. So this way you can understand how it works. So as you can see, this you can call it the operation table. So this shows that this gate is working as a NOR gate. All right. Sorry. It is working as a NOR gate. NOR of A, B. And you will also see that for a parallel structure here, you have a corresponding series structure over here. That is very important for this sort of circuits to work properly. So you have a complementary kind of structure. If it is parallel here, it will be series over here. All right. So that is how this works. So let me give you a little exercise. Why don't you construct a similar table for this? So Pabitra, can you just tell them how to use that class notebook?
Yes. So what you have to do is that see, you can draw your circuit on a piece of paper. You take a photograph and you see there is a class notebook available in MS Team. You just paste your photograph there. You just upload your photograph there.
So you don't have to draw the circuit because circuit is already there. I just want you to make this table, this kind of table.
The circuit is already there.
So for this circuit, you just make that, you can say the operating table. So why don't you just do it in your notebooks and.
So the thing is that you have to look at this circuit and make the operating table in your notebook, just a small table, and then you can just post it. You just post it in the channel.
Yeah. So please do it. It will take you a.
Yeah, you can immediately right now you can do it.
Yeah.
You first draw the circuit or look at the circuit.
Is there. Circuit is there. You just need the table. That's all.
You just find out the table. CRM, I think the circuit is getting obstructed. Can you just?
I think the required circuit is shown. Yeah.
Okay. Yes, required circuit is shown. Yes. So you just draw this circuit, and then you make the operating table. You understand what is the operating table? It will be for each values of A and B, high and low. What is the what is the output?
Kind of table. This kind of table.
Exactly. This is the operating table. So you similarly denote values for P1, P2.
So the upper two transistors are of P type.
Let me just label this. This is P1. This is P2. This is N1. This is N2. Yeah.
Yes. I think you have your answer.
And this is out.
You draw the table, take a picture with your mobile phone and post it.
Yeah. Are some of you done? Then just post it. Then hopefully we can see it. So has anyone posted?
Not yet, not yet. So what you do is that anybody, you just make this table, take a picture, and in the general, in the MS team, you just post the picture. I think all of you can write there, so you just post the picture. We'll find out who has done it. Any of you just quickly draw a picture and then
It's just a simple table like this one. So yeah, please just like this one.
you'll have 5 columns, 4 columns for A, B, oh no, so more. A, B, P1. You have columns for A and B and P1, P2, N1, N2. 6 columns and 1 out column, which is either low or high. And these inputs can be low or high, and these gates P1, P2, N1, N2 can be open or closed. Yeah, somebody has.
Yeah, okay. So how can we see that? So should I stop presenting? Yeah, should I stop sharing? How can we see their post? Hello? Pavitra, are you there?
Hello. If you go to the other window, there are two windows of MS Team. You go to the other window.
I have only one window. I don't know.
No, see, there is one.
You can present and show. I mean,
yeah. Should I present and show?
Yeah,
okay,
yeah,
I'm doing it. Yes. So everybody can see. I have clicked. Yes. Now can you see?
Yeah, I can see.
Yeah.
All right. Okay. So what kind of a function is it? Can anyone tell? I mean, it is obvious, of course, but
so the answer was given by wait, let me see. This is Srijan Das.
Yeah. So Srijan, can you just tell what kind of you have shown the operation table, but what kind of a gate is it? What kind of function? Of course,
the NAND gate.
It's a NAND gate. Okay, it is shown there anyway. Yeah. So now you basically know how to analyze it, right? It's not very difficult. So I think we are done for today. So there are a few more circuits. I think we can take those up in the next class tomorrow. There is, isn't it? So we'll take those up in the next class. All right. So I think we can stop here today, right? Pavitra?